Hi guys, let's do an example of disordered solvent on special positions. I added this structure to this week's data folder on Dropbox. It's under tall underscore resi 1, I think. It's not a required problem, but you'll be able to play with this if you wanna try this out. I'm gonna start as usual by opening the ints file and at the same time running one refinement just to see how everything looks. So one thing that I noticed right away is this takes a while to run. It's a bigger structure than we're used to working with, and this is not so unusual, but we can do something about it. We can change least squares refinement to CGLS, which is constrained gradient least squares. It doesn't work as well as full matrix least squares, so we need more cycles. I'm going to go from 5 regular least squares to 20 CGLS cycles. But even with 20 cycles, I have to take ACTA out because this is not really an approved way of doing this. 20 cycles still goes a lot faster. So we're going to stick with this until the structure is almost finished, and we'll go back to regular least squares to generate the final file for publication. So let's take a look at the result here. The structure is pretty wacky. It has some features, honestly, that are unexplained even after looking at it for a really long time. But the actual chemistry, we're not going to focus on it here, especially since it's totally mysterious to everyone. We want to focus on the disordered solvent instead. The first thing you're going to notice is when you look at this without growing the structure, this disordered solvent looks like absolutely nothing. Like I don't know what this is. This I could imagine as a piece of a toluene molecule. This I don't know what it is. When we grow it out, everything is going to look a little more like it should look, although still not very easy to interpret. I'm going to pick one of these, and we'll start with this one, just out of a desire to start somewhere. I'm trying for one of the strongest or most distinct looking solvent fragments, just to get the biggest Q peaks out of the way at the beginning. So I can maybe pick out a toluene molecule here. This looks something like a toluene. It is apparently on an inversion center. The structure is in p-bar 1, so the only symmetry elements are inversion centers. We can confirm this by typing echo ccrd cell, and the centroid is on 0.5, 0.50, which is an inversion center, so that confirms our guess. We're going to model this using a fragment from the library. So I'm going to go to my web browser and navigate to Ilya's fragment library, which is the IMGL that I mentioned in class. I'm going to scroll down to toluene. Oh, this was crystallized from toluene. That's important information. I'm grabbing the frag command here, and I'm going to just notice quickly up here that the numbering scheme starts with C1 as the methyl group, and then proceeds with C2 and around the ring to C7. Okay, I copied these coordinates, and I'm going to go into OLEX and press Control V. I'm going to zoom out to find my toluene, and shift click and drag to drag it over near the fragment that we want to fit. I'm rotating this until it looks about right, and then I'm clicking on atoms in the fragment and corresponding atoms in the difference map. I'm clicking on 2 or maybe 3 of those will get it lined up pretty well. It doesn't have to be perfect. I'm hitting escape a bunch of times. It's going to kill the Q peaks that are right on top of our new fragment peaks, but That's not important to us one way or the other. We've got these coordinates, and that's all that we needed from OLEX. Now I'm going to come back to our ints file. I'm going to go down to the bottom. Below the last existing molecule, I'm going to make some space. First, I'm going to paste the fragment that we got from the internet, and then I'm going to type resi, tall capital letters. I'm going to start with residue 21 because I already used the lower numbered residues for the other bits of this structure. I'm going to type affix 176, which corresponds to fragment 17. This is on a symmetry element with multiplicity 2, so that means the occupancy is going to be 1/2, and we need to put it in a negative part. So this is going to be part -1, 10.5, and I'm going to type out our 7 atoms now. C1 is the methyl group. C2 is the ipso carbon. And C3 doesn't matter, I can pick either one of the orthocarbons. And then 3 atoms define the orientation of the fragment, so the other ones I can just fill in zeros. And then the 3 tags that I started this with, I'm going to close them in the opposite order, and that just makes it easy for me to keep track. So first part 0, affix 0, and resi 0. Okay, let's save this, run a refinement, and see if this toluene stays where it belongs. How did we do? Okay, it stayed where we put it, and the ADPs look reasonable. We're going to have to remember to have some tolerance for strange-looking ADPs when we work with these fragments disordered over symmetry elements, because it just is intrinsically a less stable situation. So this big methyl group, I might be disturbed by that under other circumstances, but that's fine for this situation. And since we've got that fragment roughly in place, I'm just going to leave it here for now and we'll move on to the next one. And here's an example of how this overlaps with its own symmetry equivalent in the in the refined structure. Okay, let's move on to the next one. This next fragment looks like it has the strongest difference features. If I grow it out, it looks like pretty much the same deal with 2 toluenes kind of facing each other over an inversion center. So I'll show this one. We can double check what the coordinates are. This is also on an inversion center, as we pretty much expected. So let's come back and get our toluene fragment again. We'll paste it in, zoom out enough to find it, zoom in, orient it roughly, and then click pairs of corresponding atoms to put it where it belongs. Okay, that's reasonable. It's close enough to try the refinement and hope that it'll go where it belongs. So this is exactly the same deal as before, and I'm just going to copy this whole block of atoms change the number and change the coordinates of the 3 atoms that we put in. We'll save this and try the refinement again. I noticed that the R factor dropped a lot after we made that change, and we can also see that the highest peak has gone down by about a full electron or so. So those are good signs. We'll take a look. How did that do? Here's our fragment 22. You'll notice that the residue number gets appended to the atom name when you look at it in OLEX. This molecule looks totally happy. It looks just like it doesn't even look like it's disordered. Although, of course, when we grow it out, we're going to see that it has that characteristic toluene on an inversion center situation going on. Now we'll go to our last disordered toluene, or I should say our last major position with some confusing stuff going on. This looks a little less easy to figure out what's going on. I can see maybe one very disordered toluene pointing off to the side like that. That's not quite on the center of the symmetry element, but if this was a toluene, then it would still have to be in part -1 because it couldn't coexist with this other possible position of itself. This putative methyl group that's kind of sticking off the side of this group of Q peaks, it's not very intense. It's 0.9 electrons. That means even after you account for the multiplicity of the position, it still is probably not a fully occupied carbon atom. We would be looking for about 3 to 4 electrons if that was the case. It's less than 1 electron, so we might have 2 independent disordered positions here. I'm going to use an OLEX trick to try to get a little more information here. I'm going to click on the map function under the work toolbar. This is the real Fourier map, which the Q peaks that you get are kind of attempting to approximate. Green is positive features, so we're looking at only positive electron density here. It might help your thinking a little bit when you're trying to figure out what a fragment is, but in this situation, it's still a little hard to decide what constitutes a molecule. I'm going to take a guess that maybe this is a methyl group, and these 6 are a very distorted ring in maybe, hopefully, the major position of this disordered toluene molecule. So I'm gonna take our fragment from the library and just kind of stick it in there very approximately. Oh, what happened there? Well, Lex really didn't like something I did, so I'm going to come back and reload that. Okay. We can show this only as before. I'll paste that molecule in. Okay. Now everything is fine. And like I said, this is more of a guess than anything else, but I'm going to try sticking this, I don't know, approximately like that. We'll just let this refine and see where it goes. And maybe by getting a reasonable fit of one of the positions of this toluene, it'll help us locate the other position. Okay, and I hit escape a bunch of times to get out of mode of fit. All right, let's copy another one of these. We're going to make this toluene 23. And we'll get the coordinates of the first 3 atoms as before. Oh, that's, well, this would be a potential problem if this atom was not part of a rigid group, but the instability of putting an atom on exactly on a symmetry element shouldn't be a problem when that atom is part of a rigid group. But just to be safe, I'm going to manually move it a hair off that position. So I just added a couple thousandths to a couple of those coordinates. And we know that these starting positions are approximate anyway, so it doesn't hurt anything to move one of those atoms just a bit. I'll save this, run the refinement. We can take a look and see how this turns out. Okay, you know what? This is obviously not great, but it's not awful either. Most of these atoms I can tell by their ADPs are reasonably happy. I'm going to change over to balls and sticks mode just so that these atoms take up a little bit less space. We see this atom sticking out all by itself. It pretty much has to be a methyl group of a second position of the toluene. There's nothing else. If it was the other end of a toluene molecule, then you would have a couple more atoms over here and over here. So it has to be a methyl group, as long as it's not a whole different molecule. We'll start by trying to model it as a toluene, and we'll do that the same as before by just pasting in a fragment and see what happens, see where it goes when we run the refinement. So I can hardly see any of the rest of this molecule, but I might guess that a couple of these Q peaks are part of that molecule. So we'll try that. I'm gonna do something here so that Olex doesn't cause problems for us. The part that we had here already is in part -1, and when you paste a solvent molecule, Olex is going to try to put that in part -1 as well. So while I still have this selected in mode fit, I'm going to type part -2 so that these molecules don't step on each other. Then I'm going to hit escape. I'm going to select part -1 and kill it just to get it out of the way. And now we've got this molecule that we can take the coordinates from. Okay. Now, we need to think about the occupancies of these parts. We're modeling it as a 2-part disorder, so we would normally use part 1, 21, and part 2, -21. But in this situation, like we discussed briefly in class, each one of those positions is further disordered over the symmetry element. And that means each one of those occupancies has to be divided in half. So now we're going to use part -1, 20.5, and part -2, -20.5. And those two occupancies are going to add up to 1/2. And then after transforming over the symmetry element, you get a total of 1 toluene molecule. So For the first one that we put in before, I'm going to change this occupancy from 10.5 to 20.5. And this is minus 20.5. I'm going to go up to my FVAR line, but I forgot to take this out when I undid all my work to make this practice structure. So I'm just going to make sure that there is an FVAR2. I'm going to search and make sure that part 21 isn't in use for anything else, and it's not. You don't want your free variables reused for multiple things. What else? We need to put in the coordinates of the second position. So we'll do the first 3 atoms as we've been doing. Okay, let's try this refinement. Duplicate atom C1 in residue tall 23. I changed the wrong molecule. Let's undo all of these. And furthermore, I also forgot to change the name of this new residue. So I'll change this to 24. Unfortunately, these 3 atoms that I did before, I'm just going to have to do them again, but that's okay. Okay, now let's try it. How are we doing? Oh, we have a crazy blob here. Why did this happen? It happened because I forgot to change the part number for the second part. The ADPs don't look so incredibly unhappy, but it's obviously not right how everything is trying to bond to each other. So we'll put this in part -2. Save it and run it again. And now let's see how everybody looks. This is semi-reasonable. It's hard to know the difference between the model is basically right and you're just struggling with the instability of molecules on special positions, or is the model basically wrong. So let's show only this part. The second part that we just put in, this looks very, very reasonable. Let's grow this out. I'm going to use pack because sometimes grow works and sometimes it doesn't. Now I can show this only. I would argue that the first molecule that we put in is probably not in exactly the right position. I can see, well, let's look again at which atoms are not doing too well. The 2 metacarbons and the ipso carbon on this toluene aren't too great, and then the paracarbon and the 2 orthocarbons, they're okay. I would like to try making just a little shift here so that this paracarbon goes on this Q peak, and this methyl group goes on this Q peak. We'll get part -2 out of here. We'll select part -1. Put in mode fit, and I'm just going to do this by hand. This is, it can be a little tricky getting these molecules to go where you want, but you can just struggle with it until it goes where you want it. That hopefully is going to be close enough. Let's fuse this, get the coordinates, and we're going to go back and change residue 23. Okay, let's run this refinement. Something blew up there. I have these maximum shifts of star angstroms. That means it went probably flying into space somewhere. There it is, it flew off into space. Okay. There might have been a typo in my coordinates, there might have been something else going on. That molecule was not apparently too happy to begin with, so maybe it's fine that it flew away, and we can take this opportunity to try to find a better position from it, a better position for it in a more systematic way. So we can do that by removing the whole molecule from the refinement and going down to the second position, which we were not too unhappy about, and turning down its occupancy artificially to maybe 1/4. Let's run this refinement. Okay. Here's the bit that we're concerned with. We do have some more definite Q peaks now, so that should be helpful for us. This shows Q peaks that look a little bit more like a toluene molecule. I can see a methyl group. Here's one carbon. Here's a couple more. I can see the whole ring here, really. This is promising. We'll get our molecular geometry again from the library. We'll paste it in here. That's pretty good. And hit escape a bunch of times. Well, I was going to get the other one out of the way, but it's not really in the way. Okay. We'll put this back in the model with the new coordinates. Okay. Oh, you know what? I forgot to undo the change that we made to the occupancy of the second part. We have 20.5 up here, so we should have minus 20.5 down here. How we doing? This is reasonable. We still have some Q peaks here. They're in a pattern that's pretty hard to understand, but we're doing okay. And the biggest Q peak near these features is I'm not sure what it is, but it's less than 0.6 electrons. So that's very decent. Let's come back and try to make an anisotropic model for our toluenes, and we can also add hydrogen atoms to them at the same time. So we did ourselves a big favor with the residues, because now I can do all the hydrogens at once. H fix tol, remember that it's uppercase, 137 for the methyl group C1, and H fix underscore tol 43 for the sp2 CHs, C3 through C7. Okay, I just discovered that an anice instruction in the same format doesn't work for some reason, so I have to put that down here. The next 28 atoms, we're going to make them anisotropic. And a rigu instruction would probably be a good idea, and we can put that down here too. This rigu underscore tol C1 through C7. We'll save this, run the refinement. And I'm looking for all of our toluene molecules to see how they turned out. This one, the ADPs look great, all things considered. We expect some degree of instability or just strangeness in some way. So keeping that in mind, these two toluenes look wonderful. This extra disordered situation down here, the ADPs turned out a bit more unstable, but still not awful. The less occupied of the two parts of this disorder came out with the stranger looking ADPs. Maybe if I grow this, we'll be able to find some reason for that. Oops, I just want one of those. This very flat atom, it's pretty much overlapped with a couple other atoms that are generated by symmetry. When you have a less occupied atom overlapping with a couple of more occupied atoms, it's not too disturbing that the ADP would go crazy like that. So how should we deal with that situation? Here's another atom that's pretty strange looking, and again, that's overlapping with some others, and it's in the less occupied position of this toluene. I'm going to deal with this situation by just modeling the less occupied one with a group isotropic ADP. That's a little bit of a we might be treating it a little callously, but it's not a crazy thing to do. And again, we're aware that we should expect some instability of those ADPs, and so if we have to do something a little strange to stabilize them, we're not going to lose any sleep over it. I'm switching these two residues 23 and 24, just because it's nicer, it keeps you organized to have the more occupied one coming first. And in this example, we have residue 23 right now is the less occupied one. So I switched them, and now residue 24 is the less occupied. I'm coming up to our anice instruction, and I'm changing this to anice 21. So only the first 3 toluenes are going to become anisotropic. And for the 4th one, I'm going to add a group isotropic ADP after each individual atom. So after the coordinates, we have the occupancy and a new free variable that will be the ADP. That's going to be, let's look at our fvar line. We have 3 in use already, so this is going to be the 4th. Okay, let's save this. We'll remember to put in a new free variable for that group ADP. Let's run this refinement and see how everybody looks. Okay. So now obviously the group ADP of that less occupied position, it refined to a reasonable value. We're happy with that. The ADPs of the more occupied position, they're oops, I didn't exchange the part numbers here. The ADPs of the more occupied position, they're all totally reasonable. This all looks pretty good as far as the disorder model is concerned. So the last step that I'm going to take right now is some quick housekeeping of putting these part numbers in the order that we would expect them to be, where part -1 comes first, and running a least squares refinement to finish this work, and getting rid of the faster but less accurate CGLS refinement. We'll do the least squares by backing up the ints file that we just ran. I'm going to say, we're going to make a note to ourselves that we finished modeling toluenes. And now I'm going to copy the res file over to the ints. That means we get to keep the results of the refinement that we've been doing. And reload my ints file. Oh boy. So I made some changes and I didn't save them. Thanks, Vim. We should save those changes. I'm going to save it, say yes to that, run this refinement. The only change is I changed those part numbers like I mentioned. And now everything that I did before, I'm going to do it again. Okay. And now our res file is our new ints file. And we can see that we have anisotropic ADPs for our first 3 toluenes and a group isotropic ADP for our last one. I'm going to come up to the top here, replace CGLS with least squares, and give it 10 cycles. I'll put an acta instruction. Save this and run a new refinement and hope for everything to converge. I'm watching the maximum shift over ESD numbers to keep an eye on the convergence. Okay, it got almost there after 10 cycles. it got down to a maximum of 0.2 shift over ESD. We'll look at this structure and make sure that nothing changed after we ran more cycles. Maybe a few of these ADPs are a bit different than the last time we saw them, but nothing to be concerned about. And the final job of reaching full convergence, I'm going to leave that for you to take care of yourself if you care to. But I hope that this has been a helpful example of using the residue function and using negative parts and finding the positions of disordered solvents. Okay, thanks for watching.